All right, we're at section 35.2, um, curved mirrors, spherical mirrors, um, images formed by spherical mirrors. And then I'm going to break it up into two parts. There's concave mirrors and there's convex mirrors. Just for a quick, I hope I get this right. This is a convex mirror here. This is typical of what you would, not typical, I mean, it's much bigger what you have, like a shaving mirror or a makeup mirror that it's concave and you look at it and your face is much bigger. And this is a convex mirror. You see convex mirrors, you see them like at the aisles of shopping shopping centers, so that you can see kind of around corners so that you don't hit anybody with a basket, those types of things. You also see it in parking lots so that you can see oncoming traffic. In fact, the image I show is of a parking lot. It's not my image. I got it off of Flickr. But let's share the screen. Here are concave mirrors. Let's make sure that we're at the right spot. Yes, we just finished the quiz. So you have a concave mirror here, and the mirror is, the reflective surface is on the inside curvature of the mirror. You have the principal axis here going through the center of it. You have the center of the curvature. This is the center of the curvature right here. And you have a radius. The mirror is curved to a particular radius. Now let's read the little square. The rays diverge from zero at small angles. They all reflect through the same image point I. So that you can see from here, it goes through here, and just as the incident, the reflection angle is equal to the incident angle. So theta equals theta prime. And that'll be true for all of these cases. And all of these reflections go through this image point here. These dashed lines are local to the particular surface, a local being perpendicular. And so you get an image here at the inside. Okay, now these are for paraxial rays, the small angles, rays of small angles. The reflected rays intersect at different points on the principal angle. So you can see for the small angle, they reflect right here at the focal point. This actually doesn't seem to be drawn to scale, because these almost look like more like the focal point, but that's incorrect. These wide angle reflections miss this image focal point, but the image point. But for small angles, you will get it right at the focal point. Now, so here's a concave. Here's how we construct the image. You can see this is the object. It's an arrow, H. It's a gray arrow, H. And this is the image, H prime. It's inverted, and it's pointed, it's inverted, and it's smaller. And as you move this object this way, this image will move this way up to a point. There's a point where when you get to the center of curvature, you get like a magnification of 1. As you start to move closer and get to the focal point, things distort, and it gets really really big, and then it reverses. It becomes upright, and it starts to magnify. Now, I've got a little video that demonstrates that that I'll post after this lecture video. Let's see. So the tangent of theta, the tangent is opposite over the adjacent. So the tangent of theta here is h over p. The p's down here. So the tangent of theta is also equal to h prime over q. Here's the h prime, here's the q. So this tangent h over p, this tangent theta equal h over p is talking about this pinkish red triangle. The tangent theta equals minus h prime over q uh, is the yellow triangle. It's minus because the h is inverted. And the magnification is h prime over h, which is equal to minus q over p. Okay, let's continue. Tangent theta, which is tangent theta of this is minus h over r minus q. Now we're talking about the little kind of aqua, greenish aqua. I'm not very good at colors. My wife could tell you exactly what color that is, but it's minus h over r minus q, and again minus h because it's negative. And tangent theta is also equal to the large H over P minus R. Now, which is the, I'm sorry, tangent alpha. And they're talking about this angle here. So they're talking about this triangle here within the red. And you can see, so it's the opposite H over the adjacent. Well, the adjacent is P minus R. That's just this section here. Hopefully you can see the little cursor going back and forth. So H prime over H is equal to minus R minus Q over P minus R. And you end up with P minus Q over P minus R equals Q over P. Now they take that equation and they come up with 1 over P plus 1 over Q equals 2R. They don't go through the algebra. I've gone through the algebra. And for extra points, this is a test to see if you're really watching these videos. For extra points, you can send me it's just simple algebra, an algebraic, the algebraic steps needed to get from P minus Q over P minus R equals QP to this equation, 1 over P plus 1 over Q equals 2 divided by R, where R is the radial distance of curvature, the curvature radius. Now, we'll also learn that the focal point, F, is equal to radius over 2. So this will become 1 over P plus 1 over Q is equal to 1 over F. So for the extra points, I want you to go from this equation here and arrive at 1 over P plus 1 over Q equals 1 over F. So let's see how many are paying attention to the video. Okay. When the object is very far away, the image distance Q is approximately R over 2, which is F, the focal point, where F is the focal length of the mirror. If you look back at this, if this is very large, it's an inverse relationship. So as P goes large, 1 over P becomes very small. So 1 over Q is equal to 2 over R. Well, you inverse that, Q is equal to R over 2. So then that's where they get this box. Okay. So 1 over P plus 1 over Q equals 2 over R. As P approaches infinity, 1 over Q equals 2 over R, which gives you Q is equal to R over 2. And that's the focal length. F is equal to the radius divided by 2. So F is halfway between C and the reflecting surface. So 1 over P plus 1 over Q is equal to 1 over F. So that's just this equation substituted instead of 2 over R, it's 1 over F because F is equal to 1 over 2. Now, practical application, a satellite dish. And satellite rays are the electromagnetic waves, just as light is, and comes from a satellite that's very, very far in the distance. So the rays coming into the satellite dish are all parallel, similar to what you would see in this image here, these blue rays, and they bounce off of the dish and are all focused into this receiver here. I've got a little video where I demonstrate that um, uh, the image of a candle. Um, if you take the image from the candle, you can see that the image of the candle is at the focal point. And I will add that um, to the video after this particular video. And you can see how right at the focal point, you'll get the you'll get the image. I got one of my cats joining me. Hello, Suki. It's not time now. Sorry about that. I think that does it for you. Yeah, we're gonna talk about convex mirrors next, and hopefully Suki will leave me alone. Right? You want to say hi? Okay. Uh, go go away. Uh, let's stop the share and stop the video.